Hey there! So I thought now we're about at a good place where we can look at some more case studies in both structure and stratigraphy and seismic data. So let's get started. So what we're going to do now is we're going to look at how using the seismic amplitude volume that we start off with, and then also the seismic attribute called coherence, can help us interpret structure and stratigraphic features. And I've talked about coherence a little bit. So let me just talk about it a little bit more, and I'll be talking about it a little bit more later on when we talk about attributes again. So when we're doing these multi-trace analyses, what we're doing is we're comparing one trace to its neighbor. And so in this case, we've got our pink seismic wiggle. Okay, so you can imagine we've got that one wiggle in a large 3D volume, and we want to compare it to the wiggles around it. And we want to understand how similar it is to it. So when we talk about coherence, how coherent is it? How similar is it? Similarity. Variance is another similar method that's great for edge detection. So how much do they vary to their neighbors? And so you can calculate these in many different ways. You can compare it to its 3 closest neighbors, its 9 closest neighbors, in a box, in a circle. So most software programs that you would use for seismic interpretation and attribute calculation will give you a lot of different parameters that you can change, hopefully. Hopefully they will. So anyway, so we're comparing our wiggle, our pink little wiggle, to its neighbors, and we're seeing how similar it is. If it's very similar, then we're probably looking at something that's very geologically similar. If it's quite different, then it is probably geologically different. And so these are really, coherence is one of my favorite attributes because you can use it for QC methods to understand your seismic volume. You can map, see faults, fracture zones, channels. You can see a lot of features really clearly in coherence. And so I'm going to start wrapping in more examples with coherence in these lectures. Okay, so just a comparison of how it works. So we have our seismic trace. And then when we're comparing it to windows nearby, we may have a little kind of shifted window where we can compare it. So we can not only change how many neighbors we compare it to, but we could look at how much it shifts. And so this could help account for different dipping structures. So you can window it 4 milliseconds or 10 milliseconds or 20 milliseconds, even though that would look kind of smeared. And so we compare it to its neighbor along a little bit of a time shift, and from it we'll be able to get the maximum coherence. And so this is an example of how it would work if we're doing that cross correlation, comparing it to its neighbors. Okay, so faults. Let's jump into faults now that I've explained coherence. So here's a seismic amplitude. This is a really classic example from 1995 and one of the first applications of coherence. And so we're looking at a time slice at 1200 milliseconds, 1.2 seconds. And if we were to look at it, and let me pop on my pointer again, I'd be able to, as an experienced interpreter, be able to pick out some interesting features here. So I could pick out some discontinuities in here, maybe over here and over here. This looks like salt to me, and I know it's the Gulf of Mexico. I could pick out a few more faults over here, and then there's something interesting going on in this upper right hand corner. But I'm going to say, I'm fairly confident, but not 100% confident. And so if we take the couple of minutes that it takes to run a coherence volume, we can end up with an image like this. And it's just like, wow, why don't we do this all the time? A lot of times coherence may be the first type of seismic data that I look at. Okay, so this is for the same time slice. And now we can clearly confidently interpret a bunch of faults. Okay, so we could see a lot of faults in this area. We could see those radial faults that I talked about, we'll often see with salt diapirs and shale diapirs. There are some faults up here. But what's interesting is that we actually start seeing this kind of interesting feature up here. So it's not as predominant as the faults and the salt, but we kind of see what looks like a bird's foot delta. So coherence is actually able to pick up oftentimes the variation between, at the edges of channels and different channel architectures too. All right. Here's another example with more modern seismic data. So this is up in the Norwegian North Sea. Just looking at the coherence data, where we've got a salt stock right here, and then we've got some lovely radial faults coming off of it all the way to the end of the 3D survey. So just another example of coherence. And then here's one more from that same paper and study where we've got the seismic data. We can pick out right here and here some of the faults, and we can interpret those. And I apparently forgot to put the coherence volume in there. So I'll have to go back and do that later. Okay, besides faults, other interesting features I thought I would talk about today are igneous features. And so this is an image of a mapped horizon along the top of the core volcano in the Taranaki Basin offshore New Zealand. And so when we look at this image, we're kind of looking at kind of like an inline and a cross line right now, so an intersection of the two. We can see the very chaotic, low amplitude seismic below and like kind of within the volcanic core. We've got some high amplitudes that are probably a gas chimney. One of my students before has suggested that perhaps these are multiples. We've got very continuous reflectors mapping on top of the volcano. We've got chaotic reflectors. You've got all the sediments around it, a lot going on, but you don't clearly see the edge of the volcano. So it would be very hard to pick out here. And so going here to where I think Dr. Murford mapped it a while back, you can see how we mapped the continuous kind of reflector in this area as the volcano. In this case, we have some well logs, so we have some gamma rays that we can pull into and tie to our seismic interpretation. So we know that this is volcanic because we've logged it. So this isn't just a salt dome that we're saying is volcanic or carbonate reef, both of which can appear very similar to igneous features in seismic data. So in this case, we've got the well log to back us up. And we could see once you do the well tie where exactly you would pick the edge of the basalt. Looking into it a little bit more, there's other features that we could pick out. We've got some potential mass transport deposits. Down here, we've got this chaotic pattern. It's probably like 20 milliseconds or so in thickness. Very, very typical of a debris flow. And then over here, we have some volcanoclastics. Here's another case of an igneous reservoir in China from a different study. In this case, they've also used the well logs to validate that this is an igneous feature. And you can see, even though it's kind of slightly interpreted over with some transparency, you can see that it's much higher amplitude. And they're able to clearly mark the top and the base reflectors in the seismic with where they see the volcanics kind of marked in red in the well log. All right. Here's another example in China of an igneous reservoir. In this case, we've got the clear, we don't have the well logs here, but we've got the higher amplitudes. You can see how they've used a transparency to kind of show where they're mapping that igneous reservoir. And then they're also pointing out some of the incoherent signal below it. So if you think back to Snell's law, if you reflect a lot of energy back up, that's less for you to transmit down. And so oftentimes beneath bright reflectors, you have more incoherent signals. They're also noticing a potential pull-up, and you can see they mark that with a question mark. Always good when you're not quite sure about your interpretation, but you want to make note of it. So pull-up is a case where when you're working in time, and we can see they're working in time domain seismic data, pull-up is where if you're traveling through a faster velocity material like igneous rock, the features right below it in seismic will actually be shallower in time because it'll take less time to travel through this igneous rock here than it would through the sediments around it. And so you get this feature called pull-up. Later on when we talk about hydrocarbons, you'll also see a push-down effect, and that's because traveling through gas clouds, you have a lower velocity and it takes longer relative to the sediments around it. So you often get a push-down effect in the presence of hydrocarbons. Okay, A few more images or from that igneous reservoir in China. So now they've done some time slices. Okay, so we're looking at it more in map view at a certain time. And they're looking at the amplitude in the seismic, trying to see where that conduit is. So we're shallower, and then we go a little bit deeper and deeper and deeper off to the right. They're looking at the energy. So energy is a way to measure the strength of the amplitude. It's another seismic attribute. In this case, they're marking, we've got the conduit, and then they're seeing some higher energy features off to the side that they're interpreting as pyroclastic deposits. And then they're also looking at coherence. So we talked about that a few minutes ago, highlighting both where the conduit is, more from the seismic amplitude and energy, but also some faults that are related to it. And notice that some of these faults that we're seeing in coherence here aren't particularly clear in the amplitude or the energy. I mean, I could kind of see them now in the energy once I recognize them in the coherence. So sometimes looking at different seismic attributes allows us to pick up features that then we can more confidently interpret in other attribute volumes. Okay, let's move on to carbonates for a few minutes. So carbonates are really fun. A lot of us are interested in them. They can be harder to image. They're faster velocity. And so here, just based on this cartoon in synthetic seismic from the Hart textbook, we can see these carbonate mounds that he's created a synthetic velocity model for. And when we look at the synthetic seismic in time, we see that same pull-up feature. Now a little bit clearer because we're dealing with synthetic seismic. So because the velocity is so much higher in the carbonate reefs or buildups, the energy travels through it much more quickly, and we get an artificial kind of structure, that pull-up below the carbonates. And of course, you can notice that the thicker the buildup is, compared to this thinner one over here on the left-hand side, the more pull-up you get. And that's because, it's gone faster. The energy's gone faster for longer. So just something to keep in mind. This is really important if you're interpreting deeper data, particularly like below carbonates or below salt dome. All right, so here's an example of seismic, and this is another great interpretation, a great way to make your interpretation to communicate. We've got the uninterpreted seismic data here with a cartoon of what they're interpreting below. And then up here, they've kind of mapped a few more of their interpretations, even though this is at a different depth. So this is a little bit larger of an area, it looks like. So they've kind of zoomed in right here. That dotted box is the seismic. Okay, so you can kind of see their overlay interpretation, the raw data, and the cartoon. And so this is, really a good way to show data in terms of a cartoon or an overlay with the raw data itself. And you can see these kind of buildups that they're imaging in Borneo, some of the different horizons that they've picked out as carbonates, as well as, and it's hard for us to see this in a slide format, but there's a lot of small channels that they've marked in the area too. Here's another example from that same paper, now zooming in a little bit more so we're able to see the detail, again with the seismic and then the interpretation next to it. So we've got a couple of different platform structures that they've observed. Here they've got kind of some of the wings that they're trying to point out. And even in this case, they've got a well where they've tagged one of these carbonate wings. And so they're able to validate their seismic interpretation with that well placement and with the information from the well. Here's one more example from the same study. And what I want you to focus on this time is, so we've got our carbonate buildup here on the left. We've got that well log that validates it. But when you look at the seismic data, you can actually see some of these internal reflections. So you can image that buildup through time. Okay, so it's not like salt, where once you get into the salt, it's a reflection-free or very chaotic feature. But you can image the internal structure of the carbonates and how it built up through time. All right, here's some karstic caves, and I'll have a lecture on karsts later on specifically, but just as a quick example, karsts are something that we're often very interested in carbonate reservoirs for different purposes. And these karstic caves are these little tiny high amplitude blips. Okay, and so we'll just pause and think, okay, we don't expect them to be large continuous structures. They're high amplitude because we're going from the sediments around them into more of this, null fluids filled space. And so you're going to have a very high reflection coefficient. And if you had the seafloor on here, you would expect probably for the top reflection of these karstic caves to be the opposite polarity than the seafloor. So just trying to wrap in some of those fundamentals. Here's another case of a gas carbonate reservoir in Malaysia. And what's really neat about this is they actually performed 4D, so time-lapse seismic data on this reservoir. And I'll have a lecture about time-lapse later on. But time-lapse is where you take a seismic survey at one point in time. There's some sort of production, hydrocarbon production. You can even do these for carbon capture. And geothermal for steam flooding, and I'll talk about all that. But so you take a seismic survey, you do some sort of injection, production, whatever it is you're doing, and then you take another seismic survey. And so you can observe by comparing those two seismic surveys, we call those 4D or time-lapse seismic, you can see the fluid movement through time from one time to the original time. And so in this case, they were able to, we're looking at the difference model down below. So they've got their original gas water contact. And then so that's from 1990. And then in 2001, they have their present day gas water contact. So, that's something we can also often observe in carbonate reservoirs. Here's a fun example, looking at the mixture of carbonates and basalts in the Indus Basin. And so here we're taking two faster velocity lithologies and kind of looking at them stacked on top of each other. So you had this carbonate reef built on top of the igneous intrusive center. And you can just kind of spend a few seconds looking at the subaerial basalts here. You can see the internal structure more of that carbonate bank that built on top of it, kind of this blue area in the cartoon. We've got our sediments around it, lots of channels. The intrusive igneous center is a little bit harder to pick out. It's very chaotic. And then you'll notice that with the subaerial basalts, you actually see a little bit of information, a little bit of structure with dipping reflectors. Here's an example from Kurt Marfort with a carbonate platform that has dissolution features. Okay, so here we're looking at these dissolution features are these little kind of circles. So we're looking at a time slice here. And when we look at it, adding in that vertical section, we can see what those dissolution features look like in the vertical section. Okay, so these little kind of holes or pockets. And then we can look at the data below it. And so one of the things I want to just point out here is that you can see we've got a lot of kind of noise and reflections that aren't related to geology in this case. And that's because of diffractions and the more highly dipping geologic features that the energy is bouncing off of. So you can imagine that as energy goes down into these dissolution features, it's bouncing back up and it has a more complicated reflection and refraction pattern. All right, now we'll look at channels in seismic just for a couple of slides. So you can have channels that have no unconformity, kind of like I'm showing here. And so in this case, you don't see a clear edge of the channel, so you don't see that clear unconformity, but rather you see an abrupt change in the patterns. Okay, and so you can see that happening in many of these cases with the channels. Sometimes the channel fill is higher amplitude, like I'm showing here with my cursor, or it could be lower amplitude to that which is inside of it. You can also have channels that appear with conformities. And so let's see, here we've got a few cases of channels where you could probably map the unconformity around it a little bit more clearly. What I like about this image and why I show it is because they show some of their descriptions in it again. So a harp is a high amplitude reflector that's parallel. So here we've got a harp, a couple harps that they point out. Here's another one, high amplitude parallel reflector. In these channels right here and over here, they're describing it as chaotic, variable amplitude, low continuity. And then they're describing it as channel fill. So just trying to show how we take those terms that I talked about in a past lecture and combine them for our interpretation. And so one of the things I want to point out is that, you know, we don't always have wells, but we can use our geologic knowledge and the geometries of what we see in seismic to try to understand what's going on in these channels. And so if we think about channel fill patterns, if a channel is filled with sand, like I'm showing in case 1 on the top, we often end up with a bump, okay? Because over time, the surrounding kind of lithology, rocks, mud and shales are compacted more than the sand in the channel. And so same thing, if you have a more shale filled or mud filled channel, that will actually compact more compared to what's around it also. So just a couple of things to keep in mind if you're trying to interpret what's in the channel. A lot of times often the mud will appear lower amplitude. You'll get kind of that same reflection pattern we saw in the last example with the higher amplitude, a little bit more chaotic, with a little bit of structure if it's sand filled. And so here's some examples of what it actually looks like in seismic. Here we've got a high amplitude fluvial fill of a channel. Here we've got what we often call like a gull wing shape of a mounded interior of a channel, so likely more sand filled than what's around it. And you can see some of those higher amplitude reflectors in it. And then here we've got a channel which has that kind of more sag fill, so likely more mud filled. This is another case of some channels. And in this case, we can see that sagging, right? And you can see that they interpreted this artificial structure above it. I guess it's not really artificial, as compaction related sags. So as the muds in the channels compacted, it caused the sediments above it to have more depositional space, or perhaps even if it took a while to compact, it kind of sagged and brought down the sediments above it too. Channels are really cool. I'll talk about them a lot throughout the rest of this series of talks, this lecture series, because, you know, what's really neat is that you can actually see the different channel architecture, and we have a lot more techniques with machine learning to really bring these out. And so this is just a classic example showing a channel amplitude of a time slice, and that you can actually see these larger scale deep water channels meander through time. And so you could see them in time slices and horizon slices, but you could also see it in the internal architecture of the channel. So with C, D, and E, we're looking at cross sections through that channel, and you could see the stacking and the movement of that channel as it evolved through time. Here's another case, a classic paper by Postmantier and Kola, looking at a few different features that you'll see with seismic for some channels that they were interpreting. So here we have our channel fill right in here. So we've got this kind of buildup of the channel with some levees around it. In this case, they've actually differentiated here some different channel filling sequences that happened. So you could have fill, and then you can have it eroded again, refilled, part of it refilled as it migrates and develops through time as part of that kind of meander loop features that we tend to get in channel architectures. All right, so now I just want to end with a couple more kind of interesting sedimentary features that we have seen in seismic. So this is one by Henry Pusmentier of a giant clast. So it's 100 milliseconds tall, so giant clast that has come off the shelf in a deep water slope setting. It's kind of come from this direction on the right. You could see how it created like this turbidity behind it. So it kind of came into, eroded some of these sediments or disrupted them, and then you see how it kind of fills in all behind it. So assuming what velocities you take, this could be an 800 meter wide and 100 meter tall clast. So super cool, I think, to be able to pick that out in seismic. Here's another case from Pusmentier. He's done a lot of work with seismic geomorphology, so a great reference to look at his data. And so here we've got a slide deposit on the flank of a salt diapir. So the salt's kind of right outside of the seismic. You can kind of see the edge of it. And you can see what happened during this kind of slump and slide, some of the thrusting features that occurred at the base of it. And if you look at it in a time slice with some color applied to it, you can kind of see the structure that it created. So it kind of looks like if you're from the north or a place where it snows, you know, how you get that, or even, you know, you've looked at a lot of landslides as analogs on the Earth's surface, you know, you kind of get that ridging effect, the thrusting effect. And so here's another case of a slump deposit, looking at it uninterpreted and then interpreted again. This is in the Norwegian North Sea. So we could see how they interpreted the thrust front, some of the thrusts, the slump deposits. They've tried to mark out what they think the basal surface is that it's sheared on. And when you look at it here, they're looking at coherence. And so you can see those compressional ridges in coherence. And so just to wrap up some of these quick examples, I just want to remind you to always describe the seismic first before you interpret it. You always want to use your in-context geologic interpretation. And so this is using the information you know as a geologist or from the research you've done in that basin or around that basin of what you might expect. You know, having those modern analogs are really essential. And of course, knowing your polarity and phase and, you know, the effects of the frequencies you're using. And I've talked a little bit about coherence, but I'll be talking more in the next module about how seismic attributes are really going to enhance the patterns that we're able to see. So as always, thank you for listening.